So let's talk about this last problem, the one I did not assign you. So we have in this situation water being pumped into a tank modeled by an equation. Its rate is given by an equation, so remember that's a rate, liters per hour. And then we have water being taken away from the tank with an R of t, liters per hour, but that R of t is given by a table, not by an equation. And we're also given a starting amount of water in the tank. So keep in mind, again, when we're talking about the total amount of water in the tank, which we'll get to later, it's starting amount plus amount of water added minus amount of water taken away. So let's look at part A. Part A says to estimate R prime. So if I wanted to estimate a derivative, keep in mind R prime is the one we have a table of. So I can't tell what the slope is exactly at 2 because I don't have an equation. The best thing I can do to estimate an IROC, the slope of a tangent line, is to find an AROC, a slope between 2 points. Now we have several candidates here. This point at time 0, 1, 3, 6, 8. So we would want to pick the AROC that is closest to the slope that we're trying to find. So we're trying to find the slope at 2. So we would want to pick the AROC from points 1 to point 3. So basically that would be 1190 minus 950 over 1 minus 3. And I believe that is 240 divided by 2. Well, negative 2. So my IROC is approximately negative 120. Now, when we talk about units of measure, keep in mind we divided R of t, which was in liters per hour, by t, which is hours. So my units here should be liters per hour divided by hours, or liters per hour squared. Now, look at part B. Use a left Riemann sum. Okay, left Riemann sum, left rectangles, to approximate the total amount of water removed from the tank. So if I were to draw a little picture here, you don't really have to draw a picture, but some people find it useful. The 4 subintervals indicated are from 0 to 1, 1 to 3, 3 to 6, and 6 to 8. So we got 0 to 1, 1 to 3, 3 to 6, and 6 to 8. And my points, this is at 1340, this is at 1190, and I'm totally not even trying to make this to scale. 950, 740, 700. So they want to use a left Riemann sum. So I'm going to subdivide my interval, and I'm going to use the left-hand intervals to dictate the heights. So my first interval has a height of 1340 and its width is 1. My second interval has a height of 1190, can't read my own writing, and its width is 2, goes from 1 to 3. My third interval has a height of 950 and its width is 3. And my fourth interval has a height of 740, and its width is 2. So I'll pull my calculator out to help me with this arithmetic, and I get 8,050. And I would go ahead and put units on that. That's going to be in liters. Remember the area. This was liters per hour. This was hours. So when you multiply them, you're going to get liters. And then the question says, is this an over or underestimate of the original thing? So if you looked at the points that I drew, the points that I drew seem to indicate that this function was decreasing. And in fact, the problem tells us that. It's decreasing on this interval. So you look at the rectangles that are there, I didn't draw it very well, but you know when the function is decreasing and you do an LRAM, that is going to be an overestimate. And the reason it is because R of t is decreasing. That makes all the left-hand rectangles go over the actual area of the function. So part C. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. So this is that thing that we were talking about earlier, where total amount is starting amount, which was 50,000 liters, plus the amount that was added, which would be this. That's a rate of change though, so we want to take a definite integral, and we want to go from time 0 to time 8 of that function, so w of t, minus the amount that we took away, which we just calculated in part B was an estimate of 8,050. Now that's where the estimate part comes in, is that we used a Riemann sum to estimate the area in part B. So I'm going to do that problem with my calculator now. And the number I get is 49,786.195, but the problem said to the nearest liter, so, whoops, wrong color, to the nearest liter, so that's going to be 49,786 liters. And now for part D. It says there's a time when the rate in which the water is pumped into the tank is the same. It's asking, is there a place where it's the same as when the water is removed from the tank, and explain why or why not. Now, I love this problem because it just sort of requires a thought process and a little bit of explanation. So when I look at the rate of change of water being pumped in, which is W of t, and I look at the graph looks something like that-ish, right? And at time 0, that graph is at 2,000. And at time 8, using my calculator, that graph is at, oops, that graph is at 81.52. Now, they tell you that R of t, which is this chart up here, is not only decreasing, we use that part, but it's also differentiable. Now, if it's differentiable, that means, of course, there's no like sharp corners or cusps, but it also means it's continuous. So if I were to look at the y values on this, which start at 1340, and you see they're slowly decreasing, 1190, 950, 740, 700, but they end up at 700. Oops, sorry. So they sort of decline from 1340 to 700, but they have to be connected because the graph is differentiable. So literally, because both of those functions are continuous, and because the 0 value of w is bigger than r at the beginning and less than r at the end, there has to be some point in the middle where they cross. So the answer is yes. And your explanation should include something about the fact that RT is differentiable and continuous, and W is continuous, and then a comparison of your values at 0 and a comparison of your values at 8, and how they switch places, which one's bigger and smaller. And that would be the answer to part D.